Hello. So today I have a new puzzle for you created by moi, and it is called Biohazard. And for those who don't see it, I prepared a little image here. So as you can see, I did my best. It's kind of hard to draw it, but now that I have the overlay, hopefully you'll see we've got the little biohazard symbol going on there. But yeah, so this kind of bit of a thematic puzzle here. And the idea here is you had your thermometers and you just dropped them all over the ground, and now there's a biohazard, which I know technically would not be a biohazard because some kind of chemical spill, but bear with me here. It's Sudoku. All right, so they've fallen in the form of this biohazard symbol, but also they've all broken in some way. So these are not standard thermometers. So what I'm going to do is I'm going to go over the rules, and there's a link below for you to try it yourself, as well as rules in the description. So feel free to sit through my explanation of the rules and then try the puzzle yourself. After the rules, I will go over some maybe non-obvious properties that are a result of those rules, in case you want a little bit of a hint before getting started. Or you come back and get those hints and maybe they help. And then finally, I will do a walkthrough of the solve. And obviously, since I made the puzzle, it's not a live solve. It's just a walkthrough. So with that said, what are the rules of Biohazard? Well, we do have normal Sudoku rules, so there's nothing different about that. In every row, column, and box, you need to put the numbers 1 through 9. Exactly once each. And we have these thermometers on the grid. They have a bulb end and a line coming out of the bulb end. And in addition to that, there's always a red circle somewhere on the line and not at the bulb itself. So the red circle is where the thermometer is broken. So these work like normal thermometers up until the red circle. So the way a normal thermometer works is whatever number you put into here, let's say we put a 2 here, the next cell after that cell, so as you move up the thermometer, you have to strictly increase. So this can't be a 1 or a 2 because that would be smaller or equal to this number. So we'd have to be higher than that. Let's say we choose 5. They don't have to be consecutive. And then we have the break. And you can see where we have this break, we also have a greater than sign. It's just kind of rotated to match the line itself. But the greater than sign always says that this cell is greater than this cell. And actually, in addition to that, there wasn't a good way to sort of make this cosmetically. But the rule is that this cell here that's broken with the red circle is always exactly 1 less than the cell before it. So instead of increasing, we decrease, and we decrease by exactly 1. So in this case, we're forced to put a 4 here. And then from there, the thermometer continues as normal from this cell. So we could then do, say, 7 and 9. So it just has to be bigger than the red one. And so those are the rules. And this is an example thermometer for you. This probably isn't the solution. I wouldn't depend on that. So yeah, those are the rules. And if you want to get started now, feel free to think about the rules, try to get started. You can always come back if you want my little hints. And then, of course, you can always just stick around and watch the walkthrough. So again, there's a link down in the description if you would like to try my puzzle. All right, so what I really want to point out about these broken thermometers is they aren't as broken as they seem. So we're going to talk about degrees of freedom. So for a regular thermometer, let's ignore the fact that there's this break in it. Let's use this long one just as an example. You can sort of figure out how many degrees of freedom the thermometer has by how many cells are in it. So this thermometer has 6 cells in it. So if you do 9 minus 6, you get 3, which means there's 3 degrees of freedom. So if we were to start at 1 and move forward, increasing by 1 every time, those are the minimums on every cell. And then we have 3 degrees of freedom, which means we can have 3 more numbers above the minimum. So it doesn't mean there's 3 candidates, it means there's 4 candidates. Let me Let me put my hand in frame. There's not 3 candidates, there's 4 candidates. So that was probably unnecessary. But so that means we can add 2, 3, 4 to here, and then 3 more after the 2. So 3, 4, 5, 4, 5, 6, 5, 6, 7, 6, 7, 8, and 7, 8, 9. And so this is how you fill a thermometer. And I've shown another trick before with thermometers where you could do 1, 2, 3, 4, 5, 6, and then from the end you write 9, 8, 7, 6, 5, 4, and then you fill in the middle. But I think talking about the specific degrees of freedom will be useful on this puzzle. So this thermometer is not a normal thermometer, though. It's a broken one with this rule. So let's think about how this rule works. Well, where the break happens, we're always reducing by exactly 1. So if we get rid of these candidates here, that means the candidates for this are going to be 2, 3, 4, 5, right? And then when we move forward from there, we can sort of think of this as a new thermo starting here. And so it's 3 long, 9 minus 3 is 6, but we also are missing a degree of freedom from the start cell because it starts at 2. So we actually have 5 degrees of freedom. So this would be 3 to 8. And then this would be 4 to 9. So that's kind of how to think about that. But that also, those extra degrees of freedom are for the entire thermo, not for the whole one. So if we want to think about the whole thermo together, we can sort of think that this cell here, after we reduce by 1, is increased by 1. So we kind of have a repeat of the candidates in the 2 cells surrounding the break. So if we think about that, that means we kind of have a thermo that is, let me say it, do it this way, 4 long. So we ignore the 2, we ignore the one where it's broken and the one after that, and then we just continue like normal. So it's like a 4 long thermometer. And so 9 minus 4 is 5. And so we can sort of start by saying, well, 1, 2, 3, let's ignore these 2 for a second. 4, sorry, are our minimums. And then we have 5 degrees of freedom on top of that. So this would be 2, 3, 4, 5, 6. This would be 4, 5, 6, 7, 8, because we're adding 5 numbers. 4, I think I did that wrong. Yeah, I missed a 3. Sorry about that. The max minus the min should be 5, right? That's 5 degrees of freedom. So 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8. I'm saying that wrong, but you get the idea. And then this one starts with 4 and is 5, 6, 7, 8, 9. And then for these 2, this one always has to be exactly 1 less than this one. So we'd be 2, 3, 4, 5, 6, 7. And again, we're not doing this in context of the rest of the puzzle. I know that there's a 1 here and a 4 here. But we're not solving it. And then this one would be the identical to this one because it has to be 1 higher than this one. So it's 3, 4, 5, 6, 7, 8, at least 1 higher. And so you can see that this thermometer actually does work out. And so when you're working on the candidates for thermometers, that's a useful way to think about it, especially when you start removing degrees of freedom. So for example, if I remove this 9, I've now removed a degree of freedom from the top end of the thermo. So I've shrunk it by 1 degree of freedom. And so now the top end, I can just blindly remove the top end from the whole thermo like I would a normal thermo. And this actually does work out to be a proper candidate filling for this. So removing a degree of freedom from the end, the top of the end will remove a degree of freedom from the top of the beginning and everywhere through it. And removing a degree of freedom from the beginning of the first one will propagate through and remove a degree of freedom from the beginning of the last one. And so the breaks aren't as crazy as you might initially think. Now, where the break happens does have interesting effects on the puzzle, but they always have the same effect of delaying our increase by 2 cells. All right, so that's the hint I wanted to give. And this is your last chance to try the puzzle yourself if you wanted to. And I'm going to get started on the how to solve part. All right, so first thing that I'm going to point out is where can ones go in box 8. So we have this one here. It blocks these from being 1. And even though these are broken thermos, we still can't have a 1 on the line, at least not here. In fact, the only places on one of these thermos that we could have a 1 is obviously the initial bulb, as well as on the break, but only if the break is close enough to the initial bulb. So like we could have a 1 here, for example. Like we did 2, 1, 2. That should work. Or this could be anywhere higher than 1. Doesn't have to be 2. So 1 can't go here, 1 can't go here. Obviously there's no 1 in the 4. So we're thinking 1 can go here, here, and here. And we're so used to thinking that bulbs can be 1, may not realize immediately that actually we can't put 1s here, because the break is right after them, and the break has to be 1, strictly exactly 1 less than the one before it. So if I put a 1 here, what the heck do I put here? I can't type 0 in FPuzzles, and either way, Sudoku doesn't have 0 in it. So that would break the rule of the puzzle. There's no way for this to be less than this one, especially 1 less. So 1 can't go in either of these bulbs, which means we actually have a hidden single 1 here. And then these 2 1s look up here. And again, this one, we can't have a 1 on the end of this thermo. There's just no way that's going to happen. And can we have a 1 here? Well, let's think about that. This could be 1, and then this could be 2. We go, oh, well, 1 is less than 2, 1 less than 2, there we go, but we'd have 2 1s in the row, right? This would be 1. FPuzzle's even telling me that can't be 1 because of this one down here that we just placed. But even if we could do that, there's no way we're having 2 1s in the row. So for lots of reasons, this can't be 1, especially because this has to start with 2. So we could do 2 3, but we couldn't even go back to 2, right? So we have to do like 2 4 and then 3 or something. But that's not 1. So 1 goes here. Sorry for the long-winded explanation there. Hopefully you get it though. So we place those 1s, and unfortunately those are the only easy digits we're getting. So the next thing I'm going to do is actually fill in these for real. And we're going to account for the fact that none of these bulbs can start with 1. I thought that was fun to have 5 bulbs in a box with a 1 placed not on any of the bulbs. We can kind of think about that as like Biohazard level 1, right? Which means something, I'm sure. So I think it's the least dangerous. Anyway, we can start with 2 here, and we can do our calculation. So this is like a 4-long thermo, like I talked about earlier. But we also lose a degree of freedom because we can't start at 1. So 9 minus 4 is 5, but we actually have 4 degrees of freedom because we have to start at 2. So we can do 2 and then 4 numbers afterward. So that brings us to 6. And then this can be 3, 4, 5, 6, 7, but can't be 4 because we have the 4 in the box. So 3, 5, 6, 7. And then this next one has to be bigger than 3, but its minimum is actually 5 because we can't put a 4. So we've lost another degree of freedom. So we actually only have instead of the 4 degrees of freedom here. Remember, even though there's only 3 numbers, we're missing the 4. So that's 4 degrees of freedom. So now we're down to 3 degrees of freedom. So we can be 5, 6, 7, 8. And then this one here has to be strictly 1 less than this one. So we'd go 4, 5, 6, 7. But here's another piece of logic. We got a 4 in the row. So this actually can't be 4. And we know this one is strictly 1 less than this one. So if this is 5, this has to be 4. But this can't be 4, so this can't be 5. And that doesn't propagate anywhere. We removed a minimum, which propagates up the thermo, so that's already been taken care of. And so now this one needs to be higher than 5. And we don't need to calculate the degrees of freedom. This is going to be 9 and 8, right? So we just go 6, 7, 8, and then 7, 8, 9. So by the time we got to the end here, we actually are down to 2 degrees of freedom, if you believe it. After the demonstration I had before, it's a bit surprising. Now, the thing that I'm going to point out about this puzzle is it's mostly symmetrical, and I'm going to be taking advantage of that to save some time. So a couple things I'm going to do is we're starting out, we're not going to be working with the first three boxes at the start, at least. So we don't have to worry about this thermo that's not symmetric. And then the only other thing that's not symmetric is this 4 here, and then the 2 placed 1s. So we'll be careful about what effect those have. But for the most part, as we're especially working with these thermos here, we can just say we're symmetric. And so this is exactly identical candidates here. We don't have to go through that logic again. Okay, so the first thing that might pop out to you or may not is we actually have a 5, 6, 7, 8 quadruple in this row. And so the remaining 3 cells have to be a 2, 3, or 9. In addition to that, we actually in this row have a 6, 7, 8, 9 quadruple. So the remaining are 1, 2, 3, 4, 5, and this one can't be 1 or 4. Okay, so I was debating what to do next here, and I think the best thing to do is actually just to fill these candidates as well. So this is also 6 long, and so we can think of it as having being like a 4 long thermo, ignoring these 2. And so we have, again, 5 degrees of freedom. 9 minus 4 is 5, but 1 less because we have to start at 2. So again, we've got 4 degrees of freedom on top of the 2. So it's the same as this. And we're going to do both of these at the same time. And for the sake of preserving some of this symmetry for now, I'm not going to account for this 4 here. It doesn't do a whole lot anyway, but I'll remove that later. So don't get too frustrated about that. I want to take advantage of the fact that the 2 sides will be identical for some logic we're going to do later. And I just screwed these up while I was talking. This needs to be 1, 2, 3, 4, or 5. Oops, highlight both. And then this is, again, it's identical to this one, right? So this is 2, 3, 4, 5, 6. And you can see that just from the normal logic of thermos. 4 through 8, and then this is 5 through 9. Okay, so now I'm going to ask the question of where can 9 go? And this might be where you got stuck a little bit. But where can 9 go in row 4, row 8, and row 9? So in row 4, a 9 can be here, here, or here. I don't think I have to explain why it can't be on one of these bulbs. Go ahead and try it. 9 can be here or here in row 8, and then in row 9, 9 is one of these 3. Surprise, we have a swordfish in our thermo puzzle. I'm not sure how often you see that. It's a swordfish on 9s. And so what that means is that for the rest of these columns, which I'll mark blue, we can't have a 9. We can't have a 9 in any of these blue cells. Technically, this one's part of the swordfish, but it's not a 9, so I'll just mark that blue. So we just have to remember that our blue cells aren't 9, and I'll leave that highlighted for a bit. But that's especially important because it's going to remove the final degree of freedom, or it's going to remove 1 degree of freedom from the top of both of these thermos. So we can remove the 9s, 8, 7, 6, 5, and 6. Okay, so this might get you stuck again, and I promise I'll get you unstuck. So I think this is the most important observation of the puzzle. And it doesn't immediately break it open, but it really, really helps. And I tried to boil this down to the most understandable way of seeing this as possible. I do think that if you looked at it right, like if you were someone like Mark, you could see this in your head. I'm not going to make you see it in your head, though. So I'm just going to pick one of these. And again, we stayed completely symmetrical, at least for what we're dealing with here. So I'm going to take advantage of that. And just do one direction. We'll assume it works on both, or it should be provably workable on both. You're welcome to go through both if you would like on your own. But I'm going to choose a 7 here. So we're just seeing, can this end with 7? And that's a really common thing to check on thermos, because this 7 forces almost the entire thermo. So it forces this to be 6, this to be 5, and this to be 6, right? We don't really care too much about that, but it might as well show off the forcing that happens here. And so now this 6, 5 in this row removes the 5, 6 from here, and that forces this to be 7, which actually does forcing upwards to force a 9 there. So if this is a 7, then this is 7, 8, 9. And so now, and obviously this is 8. We don't have to fill all these out to see this, but I feel like seeing this isn't too hard. The consequence of this, if you think about it, is where then does 7 go in box 8? And it has to go in one of these two thermos. Obviously, with this 6 here, that removes the 7 as a possibility on this part of the thermo. I might as well mark that too while we're marking things. So, but you can sort of think about, okay, I removed 2 degrees of freedom from the top here, which removes 2 degrees of freedom all the way down from the top. And so that removed the 5, 6 from here, and that removed the 6, 7 from here. So you don't necessarily have to have all these filled to see that. And so a 7's in one of these thermobulbs. And so that means one of these red broken parts is a 6. Because it has to be one less. So if the 7's here, this one's a 6. If the 7's here, this one's a 6. And so these 7's here, I mean, a lot of stuff happens. I'm not going to go through all of it because the important part is if we look at these two cells here, now neither of them can be 6 or 7. This one's more obvious. It's directly seeing one of these two 6's, and it's directly seeing a 7 below it. This one over here, if this were a 6 or 7, that would force a 7 or 8 into this blue cell. So if this were 6 or 7, pretty clear to see this would have to be 7 or 8. There's already a 7 or 8 in the box. And again, I'm trying not to do too much removal of pencil marks here so we don't think we're bifurcating or something. But again, there's not too much to see here. So that's also a 4 or 5. That makes a 4 or 5 pair here, removing that to be a 2 or 3. But also, we removed 2 degrees of freedom from the top. So if we go all the way down our thermo, we'd be removing 2 degrees of freedom all the way down to the bulb, making both of these bulbs a 2, 3 as well. And now we have 3 cells that can only be 2 or 3, and so that's broken. So now that I've sort of walked through and shown you that, let me sort of show you that it's not that hard to see based on what we've got here. So if this were a 7, that forces a 7 to be down here because we have the 5, 6, 7, 8 quadruple. So a 7 here forces a 7 down here. And the 7 here removes 2 degrees of freedom from the top of our thermo. So that's gonna force a 7 into one of these two, which forces a 6 into one of these two. And so we now have a 6 up here, which removes the 6's from these two. We have the 7 here removing that 7, and then this obviously can't be a 7 because that would force an 8 into here, and we know that we're going to do 7, 8 like that, right? So again, I'm showing you the same thing, but I'm showing it to you without filling. So the important parts are 7 here means 7 here, which means 7 in one of these two, which means 6 in one of these two, which removes 2 degrees of freedom from this, making this a 4 or 5 pair, which propagates all the way down to make these a 2, 3. And then this one here, we're removing 2 degrees of freedom from the top, making it 2, 3, 4, but also removing the 4 because of the 4, 5, leaving 2, 3. So it's up to you whether you think that's actually seeable or not, but it's a very important deduction. So I'm going to remove 7s from those two. So now with these two as an 8, 9 pair, we can remove 8s from here, making that a 6, 7 pair. That actually forces 8 to be in one of these two, which does put a 7 in one of these, but I'm not going to put a confusing mark there. Not too important. But the 8 in one of these two actually does remove a degree of freedom from the top of these thermos. So we'll just go down and remove the top number from all these. In addition to that, we have a 6, 7 pair in box 8, which removes the 6, 7 from this cell. And this now maxing out at 5 means this maxes out at 4. All right, so now with this 2, 3, 4 triple in box 5, we actually have significantly restricted what these bulbs can start with. So let's do the degree of freedom calculation. We have, and we probably want to do these separately because their break happens differently. They both have 3 degrees of freedom though. Sorry, they have 3, they're as if they were 3-cell thermo, which means they have 9 minus 3, which is 6 degrees of freedom, but we have to start at 5, which removes 4 more degrees of freedom, so we actually have 2 degrees of freedom. If that makes sense. Because the 1 through 4 removes, not being possible, removes 4 degrees of freedom from the front, and then the 3 long thermo removes 2 from the top. So, well, 3 from the top, if you consider 9 degrees of freedom as being the start. So anyway, this is 5, 6, 7. This is 6, 7, 8. This has to be exactly 1 less, so it's 5, 6, 7. And then this is 6, 7, 8 again. And this is 7, 8, 9. And then we'll do this one, 5, 6, 7, 6, 7, 8. Or sorry, this is exactly why I want to do them separate. This is 4, 5, 6. This is 5, 6, 7. And again, if you see time and time again that the one right before the break matches the one right after the break, unless there's something else acting on it. 6, 7, 8, 7, 8, 9. Okay. So now we have a 6, 7, 8, 9 quadruple at the top. So this can be 1, 2, 3, 4, 5. This can't be 5. I'm also going to do a little bit more cleanup because we can now get rid of our symmetry here. So this can't be 4, which means this can't be 3. That doesn't have any effect later down on the thermo. So like I said, it's kind of minimal, but we might as well take that into account. So now the important thing to see, which I think is the second most important observation in this puzzle. Well, so there's the initial swordfish on 9s, which is obviously important, which then leads you to be able to check out what the effect 7 has at the ends of these. And then this is the next thing that's very important, which is this quadruple. Sorry, this can't be 1. I got rid of 1 instead of 5. Sorry, I got rid of 5 instead of 1, which is bad. 2, 3, 4, 5 quadruple. So that does a couple things. One is it gives us this 9 here. So now our swordfish becomes an X-wing. I can just, for this whole column, just remove the highlighting there. This 9 here removes 9 as a possibility from these two, so we can remove those highlights as well. And might as well make those blue. So now we just have an X-wing on 9s. And the other thing that this does in column 5 is because we have 1, 2, 3, 4, 5, 9, these remaining 3 must be 6, 7, 8. That's, I guess, a hidden triple, you might want to call it. So next, we can take a look, and there's 2 cells left in this box. I think it'll make showing this easier just to fill the candidates. It's going to be 5, 6, 7, 8, 9. And so now if we look at this thermo up here, we know that this has to be exactly 1 less than this. So this is going to be 5, 6, or 7. And so you might be seeing a few things going on here. First of all, where do 2 and 3 go in this column? Well, one of them can go here, but the other one actually can only go in this bulb. So that's a hidden 2, 3 pair. That means this can't be 8, so I'm going to go slowly over the repercussions here. That forces the 8 here. This is a hidden single 8 now. That 8 means there's a 7 here. This can no longer be 8 or 7. This 2, 3 in this cell means this is 1 or 2. I'm not going to bother putting 2 through 9 in this cell, but the one after this one has to be 8 or 9. We also have this 5, 6, 7 triple in this column, which means this isn't 5, 6, or 7, and this isn't 7. And so we now have this 8, 9 pair, this 2, 3 pair, and this 5, 6, 7 triple in this column, which is very nice. Removing the 7 here does not affect the rest of this thermo. But what we have now is a 6, 7, 8, 9 quadruple in box 2. Weren't expecting that, were you? This is really cool. So we can't have 6, 7, 8, or 9 in any other cell, including the broken cell, removing 6 and 7, placing it as a 5, which then forces this to be 6, because again, they're 1 apart. And so that actually removes 6 from this, and now we just have a 7, 8, 9 triple. 5 is removed from here, and the remaining ones here are 2, 3, and 4. So now, with this 2, 3, 4, you notice it does match up with this 2, 3, 4 here, so that's a nice triple. But we did place this 5, and so that removes 5 as a possibility from this cell. And so that does remove a degree of freedom from the bottom of these, not from this one though. Remember, we already removed the 7 there. So just got to be careful here. So 6, 7 means this can't be 6, which means this can't be 5, which means this can't be 6, but this can still be 8, 9. Doesn't make this a 9. And so now we have a 7, 8 pair in box 3, which again affects this cell, meaning it can't be 7. So this is 6, this is 7, this is 8, this is 9. This 7 means this can't be 7, putting a 6 here. So now 6 can't be in any of these places in the box. And these 6s do C down here, making this a 7 and a 6. And again, there may be different orders that you'll do this in, but that does help these thermos a lot. So this 7 means this is a 6, which means this isn't a 6. And this 6 means that this is a 5. This can no longer be 6. And so now we're left with a 7, 8 pair and a 2, 3 pair. Additionally, we placed a 5 and a 6 in this row, which removes the 5 and 6 from this cell. So this is a 4, which forces a 5 here. So we can do 9, 8, 7, finishing off all but the 2, 3, 4 triple. This 4 doesn't propagate forward yet, but the 9 and the 8 see this cell, making it a 7, which does propagate down. So now these can't be 5. 5 must be up here somewhere. And this 5 here that we placed a bit ago removes these 2 from being 5, which means 5 is in one of these 3 here. Okay, so next we're going to do a little bit of cleanup and some observations. So this 1, 2 pair here does remove 1 and 2 as a possibility from this cell here. More importantly, we have this 6 and this 6 looking into box 6, as well as this 6 here. And the candidates here, I mean, if this were 6, this would have to be 7, 8, which isn't possible based on our pencil marks. So the 6 must go here, which forces a 7 here. And then this 7 sees this, making this 8 and 9. This 8 comes over here, making this 7. And then the 9 sees over here, making this 8. We have this X-wing on 9, so that immediately puts a 9 here. And we can remove our X-wing highlight. Continuing on, this 7 here removes a degree of freedom from this entire thermo. And this final cell here, because we have this 1, 2, 3, 4 quadruple, this final cell here must be an 8. And we have created a 2, 3 pair in box 5. So this has to be 4, and that finishes off this thermo, forcing a 5 here. This is no longer 5. And this 4 sees up here. And this 7 sees up here, placing an 8. Sorry if you've been staring at that one. We have 8s looking into this box, placing an 8 here. And in this box here, now there's only one place for an 8, because this 8 sees down here, and it can't go on the, and this 8 sees here even, can't go on the thermo. So the 8 goes here. And I believe we are finished with 8s now, so that's awesome. And so this 5 here that we placed sees here, makes this a 6. This 4 sees here, makes this a 5. And then this 2, 3 pair here sees this 3 and makes this a 4. And this 1, 2 pair in this row actually does resolve this 3. putting a 4 here and a 5 here. This 5 sees our pencil mark up here, forcing a 5 here. So this is no longer 5. And then if you look at where 5 can go in box 9, it can only be here. So that is another hidden single. This can no longer be 4. So 4 is going to be in one of these two, and it can't be, this 4 sees down here, so the 4 is here. Other than that, we are missing a 7 in this box, and it should be pretty clear where that goes. It goes right here. And that, for the 6 in this row, there's a 6 in this box, can't go here, so the 6 must go here. Oh, I typed 3, should be a 6. And the rest of the box is a 1 or a 2, and so then this we can fill as a 3. And with the 1-2 pair in this box, that means that this has to be a 9. This 3 sees down here, eliminates a 3 from here. Just trying to keep up on the pencil marks here. This 4 up here sees there. And then looking at the non-1, 2, 3s again, 7s look into here and here and here. So that, I believe, is our final 7 on the grid. And so now to finish off 9s, if we look at this column here, I mean, this can't be a 3. With the 1-2 pair now, that leaves this to be a 9. And so then our, I believe, final 9s in the grid are here and here. Now this 4 here we placed a while ago, I didn't remove this 4 pencil mark, but now you can see that this is where the 4 goes in the column in the box. That 4 looks over here along with this 4 here, placing a 4 here. And so now these 4s look down into box 9, placing a 4 here. 3 in box 9, the 3 looks down here, so this is a 3, 2, and the puzzle's basically done at this point. We are just finishing up. And so this is a 1 or a 2, this is a 1 or a 3. We did place the 4 already, so this can't be a 2 either, so 2s look up into here, placing a 2 here. This is 3, 2. This 3 sees here, this is 1 and a 3. This has to be 3 because of the 1-2 pair. That leaves 1 or 2 here, and the 2 sees this, so this is 1 and 2. For this column here, we have the 2, so this is 1, 2, forces a 3 into here because of the thermo. That puts a 2 and a 3 here, which forces a 2 and a 1. And this 3 here sees down here, making this 2, 1, 2, 3, and 1. And so that is how you solve Biohazard. I hope you enjoyed the puzzle. Hope you enjoyed the solve. I think it was on the difficult side. There's a lot of things that you have to see there, and there's a lot going on in the puzzle. And in addition to that, there's the new thermo rule, which may not be immediately obvious what its properties are and how it works. So definitely don't blame you if you had to struggle a bit on that. I certainly I had some fun finding a nice, good path to show you guys for this, especially with those 7. So hope you appreciated that. And if you liked this puzzle, there's other puzzles that I've created, which you are welcome to try, which also have videos. I will put boxes on the screen. One of them will be a puzzle that I created and a video for that. And I'll put up another box for one of my other videos. And if you want to see when I post videos in the future, the best thing to do is subscribe so you can have that show up in your feed. I just recently hit 200 subscribers, so I'm very happy about that. Be even happier if I could get that higher. There is a I'm far off from it, but my goal is 1,000 subscribers. That will allow me to monetize my videos, which I don't really need to do. I have a day job, but that would certainly be nice for me. But either way, I appreciate every subscriber. I love when you guys comment. I love when you guys say how you did way better than me at a puzzle and point out an awesome bit of logic. I do appreciate that. I always like to learn more about Sudoku and how to approach puzzles and all that good stuff. So with that said, that's about it. So thanks for watching.